So we got the new UI. We'll do a quick tour, and then we'll also demonstrate the live logs and how you can use them. And so today, I'm not gonna take too much of your time. Maybe we'll talk for 20, maybe 30 minutes at most. And the idea that we want to explore is an idea that is going to be very important over time, and it's the idea of declarative programming, which is the idea of not telling the computer or the machine or the EVM what to do, but rather telling it what you're looking for, what an exploit looks like, what a property looks like, and then letting the machine do the work for you. And so as you evolve as a security researcher or you evolve as a developer, you want to be mindful of the paradigm that you're in, both mentally and also as an engineer. And the first level, the first paradigm is called the imperative paradigm, and is the idea that you would tell the machine what to do. So Solidity is a imperative language, right? You just tell it, like, you want to do 2 plus 2, you tell it that you take the leftmost number, you use the add command, and then you sum it up. And so that's what imperative means. It just means you tell it the steps. And instead, when it comes to, interesting enough, web development, and when it comes to invariant testing, we don't use imperative methodology. Instead, we use a declarative methodology. And it's, again, the idea that you specify what something looks like. So I'm going to start by sharing my screen. And so this is the Recon website. We got a couple of tutorials, 15-minute tour, 1-hour tour. So if you don't know how to use it, just go check those. If you're not familiar with the technology or the site, you just have to log in via GitHub, and that's it. We use GitHub to prevent DDoS attacks, so that's why we use it. And through Recon, you can build your own repositories through this URL right here. We'll show it in a moment. And then the new UI for building your handlers launched. You can see the live update as you toggle in stuff. It's basically adding in extra known view functions, and it's basically generating them. So that's basically what we've been doing here. And our latest and greatest feature, as I look to show you some new ideas, I look to show you just a couple of ideas of how you would think in a declarative way. So the code that I'm gonna use is called TWAP study. So if you can follow me here if you wanna copy the code. I should have a copy of it myself. Let's say it's TWAP Recon demo. I just check if it's set up properly. So TWAP study, that looks to be it. So going back to the mindset of a hacker, let's start by looking at our code and just thinking about the things that can go wrong. So let's say we're looking at this repo in general. So a couple of observations that should be fairly obvious is that the name of the contract is always the same, right? TWAP weighted observer, relative TWAP weighted observer, relative TWAP weighted observer, etc. And so the only change that you will see is that as we go from the optimized to the inline optimized to the reference, we basically have different versions of the system. So what could be, and I'm asking you, the audience, so feel free to unmute, but what could be an interesting first way for us to compare something like a reference versus an optimized version? What will be the most basic way for us to know if there's perhaps a vulnerability? What type of test could we do?
differential test.
Exactly. We could do a differential test, and the way we will do it, and I think maybe it's already set up as well. No, this is just the normal test. But so that will really be the first level. So we will start by doing the differential fuzzing, as you said. We will apply differential fuzzing, which will basically allow us to compare the functionality of the reference against the optimized. And so at the base level, what you're doing when you do that is you are comparing them, right? You would call it compare them. But what you're truly doing is you are saying, you're telling the fuzzer that the optimized must match the reference. So as we go deeper on this, let's say I do a really basic variation here. Observe, update, set value. So let's say we have the optimized, relative, and then we have the reference, observe, reference, value, reference, update. So our first level will simply be to grab both of these, uint256 from optimized, and then uint256 from reference, and then we would use our trusty T to assert, and we will verify that these match. So what is wrong with this? What is the first mistake that I made? Okay, we lost the guy. What do you think I made as a mistake? Like, what is the mistake with this check, with this implementation? As I replace all the names here, but the mistake that I made is that I'm telling the fuzzer that these two must match, but what I'm ignoring is that one of them could revert in a different way. So this is something you want to keep in mind. I guess reference is undefined. This looks fine. Let's see if this compiles. Yeah, we're using the keyword reference, which we cannot use. So let's replace reference dot, or rather reference with reference, or I guess standard. Can we use standard? So now we're missing Chimera, so that's we're used to this type of problem. Let's grab our trusty installation help. And there are mappings. We're gonna have to start with a 0 here. So the second level of our test needs to have a verification that the reverts match. So that's where expressing what we're looking for can be very different from what we think. And that's simply because all we're saying here to the fuzzer is find me an instance where this doesn't match. Find me an instance where this fails. And what we actually want is not that. What we actually want is find me any instance in which the behavior of one of them is different. And so when we talk about behavior of a function, we have more than, we actually have a big surface area. That's really, it becomes super interesting actually, because something that you can immediately think about would be the return value, which we already did. But then we would have the revert, which we have to do. And then another interesting aspect that in this case doesn't matter, but could be very interesting to explore in the wild, would actually be different gas amounts. That's because a standard version, like that would actually be a very interesting test, will be for us to actually write a test in which we pass our gas, and then we will pass this to both, and we could have a scenario where the reference version works and the optimized version fails. And so if we ever find such an instance, it means that the optimized version is less optimal than the reference. And so that could actually be an example of using a declarative approach, where we are simply looking for some instance. We just want to make sure that this doesn't happen or that this happens, as a means to elaborate whether that could create some opportunities. So in this case, we could simply assert that if this fails, the implementation is written poorly. But there are other cases where this could actually be used for example, to find a function that works even if you pass it lower gas than intended, which could be an indicator that the function, for example, doesn't check whether it adds sufficient gas, and it doesn't forward sufficient gas in some specific mean. And so the next level, as I add the try catch, will be for us to try here and catch, and I would just do the same thing here just for convenience. But interestingly enough, if we want to verify that the standard succeeds, then perhaps we would actually just do something like this, where we don't catch the standard, so only calls in which standard doesn't revert. And then we would have a false here anytime that the optimize fails when standard succeeds. So that can be indicative of a broader issue or a broader bug. And then so that can be one interesting, that could be gas grief, for example, check that we could do. Another check that we could do will be what I said before, just having two try catches. So actually we would want the values, and I guess the way we will write it would be try blah 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 catch, and then same thing here. And so this becomes optimized blah 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 returns uint256 from optimized. I guess we will do just val returns is it return? I know I'm missing the try. Returns blah blah blah. We will just get the same returns here, and then from this we can effectively assign all of these values. So from optimized, from standard, and then two bools here, something like optimize revert, and then optimized what is it, standard revert. So from optimized it equals to val, and then optimize revert here becomes true, and then here from standard equals to val, and standard revert is equal to true. So at this point we're basically comparing values and comparing reverts. So we will check from optimize and from standard, and then we will also check the revert on standard and the revert unoptimized. And so this wouldn't necessarily be exploits, but this could be interesting. So I'll just do fit meaningful tests. I will push them. I would run Medusa locally just to see that it works, just to make sure we got something worth testing. We can see blah, 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 blah. So we have a bug here. Could be our good old compile all, which we'll fix next week. And that's why you should always run the code locally, just to make sure. I guess the gas needs to be passed here. So at this point we will push a fixed compilation. We see immediate breaking of properties. We like to see that. So I guess that's gonna be a bit underwhelming when he breaks them in 2 seconds. That said, let's just do our little spiel where we will push our code to online, and then we'll go to the jobs page. You can see here we got the recent build on the 2-up study that I built, but I'm gonna do the usual stuff. I'm just gonna paste it here, set a limit to, let's say, 20 minutes in seconds. Run the job, and the job has been queued. So now the job becomes, this is the single job page now. You can see that this shows you basically the data because the job is queued, it's not running yet. You can share it by clicking this button. And once you do, this page becomes shareable to everybody. So I'm gonna share it here in the chat. And I guess we're gonna watch it as it updates, as the job goes from queued to running, and we end up getting the live logs. So we're just gonna show that. And so the thinking around this is that obviously you would ideally write something that will get you a bug, right? That's the holy grail. The holy grail is I do nothing, I press a button, and you know the machine makes me money. You know, the gambling, I just go to the casino, I put the chip in the roulette, and it prints me money. And so that will be the ideal scenario, but that's not always the case. Sometimes you can't find a bug. Sometimes there's no bug, or sometimes it's too difficult to specify a bug. And so what you can do instead is you can use the fuzzer to help you find interesting edge cases. So that's something that I don't believe anybody's doing in a contest at all. Like nobody is using the fuzzer to give them edge cases or using the fuzzer to answer questions so that they can then have scenarios. Let's go back to the code. Our code is a TWAP. So what does it mean that the TWAP reverts? Doesn't necessarily mean a lot in general. It could mean that we set the value to the maximum value, and so obviously we're going to revert, right? So doesn't necessarily mean anything. However, the fact that we do get a revert or we do get a bug is could lead us to find something more interesting down the line. And so even though by itself the and you can see that the job is running, so in a minute or two it's going to produce the live logs. And so these ideas are that we could write something really quickly that can help us validate or invalidate some of our theories. In the case of the TWAP, it could be that the TWAP accumulator never decreases. That could be a good indicator that something is really wrong. or we could have that the TWAP never reverts. Obviously, the TWAP eventually will always revert because it runs out of time. So that's something to keep in mind. Although there are implementations that wouldn't. So that's another interesting consideration. And then perhaps you could have that the time to accrue can never be more than the current block. So you can have the idea that the counter should never somehow overflow or underflow. And so all of these are ideas that can take you seconds or a few minutes to come up with, and they will not yield an actual exploit because they're insufficient. You haven't found a way to chain them. However, once the tool starts generating you cases, and you can see that it's running on the cloud and sending us update every so often, as it starts to find, you can see actually that optimize started failing when standard succeeded, by the way, which is exactly what I mentioned that would be funny. And so as we, I guess, as you find ways to express in a declarative way what a mistake or what a bug or what a condition is, and then you start having the fuzzer generate you those conditions, showing you those steps, then you are now realizing the paths that you can take as an attacker. And so that's what I wanted to talk about today, is the idea that you can use the fuzzer to find bugs, and that's always the best, but maybe it's gonna take you 2 weeks to set it all up and find them, whereas you could quickly set up the fuzzer to give you ideas or give you proof that certain things happen, and in doing so, those could be the precursor of a bigger bug. And so you can chain the fuzzer by using it in this way, by telling it what are the scenarios that you want to see more of, by telling it what a specific scenario looks like, and then you just let the fuzzer cook, you let it do the job, and you can eventually find something that perhaps can help you unlock the next level of your exploits. So that was it for today. We got the new launch. We got the live logs out now for Recon Pro. If you wanna check the new app and you find some bugs, please send them to me. And beside that, if you have any quick question, I'm happy to answer them. Otherwise, that was it for me today. We're gonna keep it short, and hopefully in a few weeks, we'll start showing you guys the bugs that we found by using the fuzzer, as some contests are made public. Yeah, live logs are available for pro customers, so they everybody gets this included in their subscription, so that you can run your jobs and then you can see them live as they update. And so this is the private page. If you don't share it, this is what the page looks like. Once the job is finished, there's also going to be the results here. Let me see if I got a job I can show. I guess I'll revert to demo. And so this is what the job page looks like for a finalized job. You're gonna have the logs on the left, the coverage report. You can download the corpus here, and we'll add buttons to download the logs and the coverage report as well. And then you can share it. And when you share it, it means that it's public to anybody. And it looks like this, so that you can watch it on a tablet or even on the phone. It looks good. So you can let the fuzzer cook, and then you send it via Telegram web. And you can basically look at the logs and see if you hit the jackpot today, as soon as you hit the jackpot. All right, so feel free to hang out if you have a few questions. Otherwise, we're gonna call it today. Thank you for attending. We'll have more next week. You guys have an amazing weekend, and see you soon.